Okay. So now let's, you read the introduction there, but the introduction is over. Now we begin to put some meat on the skewer, okay? Slowly, but we begin. Now, yeah, this is, you have already seen this, right? So we can skip this essentially, but just be aware when you're searching for something, that's something actually I probably forgot to mention, but it's important to understand that you are studying web information retrieval, right? But actually most of the things that you're going to learn, I hope, actually apply to other corpora as well. Okay, it is not that when you consider, for example, a corpus of emails, everything collapses, nothing is true anymore, and the world changes. I mean, many of the things that you're going to apply are very similar. The way you organize the corpus is similar. The algorithms you use can be, to a large extent, the same, and so on. Okay, just be aware of that. You're not just learning web information retrieval. You're learning how to retrieve information from a collection of documents, using whatever means you can. Actually, I think the take-home message here is use whatever you can. Whatever information you have there, try to use it. If you have links, use them. If you do not have explicit links, perhaps try to create implicit ones and use them, and so on. Okay? Flexibility. Okay, this is something about structured versus unstructured data, meaning relative value on one side, the volume of the data on the other side. So meaning many of the data sources you are dealing with are either unstructured or semi-structured. So they collect, so they are documents that are not always organized according to a given pattern, or they are organized according to a given pattern to some extent. And this thing has changed today. Okay? Most of this comes from web and related stuff. Market cap means money, just to be clear. So, if we want to be a bit more formal, we could say that we will very often be speaking of a collection or a corpus, which is a set of documents. And for now, we assume it is a static collection. You have downloaded it and you process it. Very often, this is changing over time. For a search engine, it is changing in the sense that on a daily basis, new documents are collected. How you combine the documents that you are collecting now with the ones you have collected in the last month, that's another story. I mean, there are some ways to do this. This is a problem you have to tackle, but for now, you can think that at any given snapshot, you have a static collection. And this is your goal. That's what you have, and this is what you want. This is the basics of the course, what it is about. Then there is other stuff which has to do with the advertising market and which has to do with whatever you recommend and so on to improve user experience and also your pocket money. So, and this is the classical search model. In the classical search model, you have something you retrieve information from, and then you have user task. What does it mean, user task? Well, the user has to do something, right? She's looking for some information. So, for example, she wants to get rid of a mice in a politically correct way without killing the mouse, actually. So, then she's going to look for, that is what she has in mind here. Now that's how she now gives sense to this idea. So you have what is called an information need. This is what you have, let's say, in your mind implicitly. This is the information need you make at some point concrete in your mind, so you can express as words. So you want to have information about removing mice without killing them. And then you have a query. So So between this and this, some context has gone missing, right? So very often, most of the queries are 2, 3 words, through 3 terms. Okay, your thought is much longer in words. So there is a first, I don't want to say loss of information, but let's say summarization, at least. How trap mice alive? No syntax, almost. There is some syntax, but not quite. And then this is what goes to the front end of your search engine. Then there is the search engine crumbling this information and the data it has, providing results. Perhaps this will bring to a query refinement, either because you perhaps change some words to really have the results you're interested in, or because the search engine itself might refine your query. For example, there are some ways, techniques to do that. It might try to, for example, find out alternative queries that can refer to different intents of the query. You know, sometimes you submit a query, but you may have different ideas in mind. Let's make an example. If I'm submitting the query leopard, am I thinking of a tank or am I thinking of a cat? That's so who knows? I mean, so this means that, for example, the search engine might return results that both are relevant to a search about a tank and about a cat. Okay? In which case you could expand the query. So expanding the query may mean, for example, adding other words that very often are related to one of the possible meaning of the term. Okay? Or simply the user. She receives a collection of results about tanks, and so she will refine the query in order to have results about a cat, a big cat, actually. Okay? Yeah. And then there is all the unsaid. So all the unsaid means the things that the search engine cannot know, but that because they are just in the minds of the users. For example, perhaps the idea I have in mind is completely doesn't make much sense itself. I will never know that, but I eventually will get a query. Or even how I express my idea is not really nicely formulated for a search engine to understand it. And this, of course, is reflected in the query you ask. Okay, so don't be surprised sometimes that your results are not the ones you were expected for. Perhaps you have to think a bit better about the query you are submitting. Perhaps you have to refine it. So then there is one general question. So the search engine has to measure its performance. How good is it doing? How do you measure that? Well, in principle, the question is very easy. Why? There is a set of documents that I'm returning, right? So, for example, just to be clear. So, oil spill Atlantic. This is the results I'm returning. Then, somewhere in the world of ideas, there is the best possible documents I should have returned for this query. Okay? When I say somewhere there is, I'm not saying that you can know the best possible set of documents you should have returned. Generally, you don't know that. You should be in the minds of the users to know that. Okay? So you should confront the users with all possible documents, and you should leave the users decide, yes, this is the right one, this is the right one, and so on. And then you would be able to say, okay, how well did I do with respect to the ideal set of results that the users would have liked to see in the first, say, 10 positions? So what do you do? Sometimes you do user studies. For example, search engines are doing this all the time. For example, you pick users and you ask them to submit queries and then rank the results that they get. Okay? So that you have what is called the ground truth. So the things the user would have liked to see, and then you have against this the things that you have returned to the user. Then you can compare the two sets. Is it clear what I said? You are free to say no. since it's important if you say, no, it's not clear. Huh? Then I will assume that everybody...
Can you explain I didn't quite understand
the last part.
Yeah.
Good. So, you have a query, right? Then the search engine returns this document. How good is the... Let's consider just the first 10 documents, so the first page. How good are these with respect to the user's needs? In principle, to know this, you should know which among the 10 million or so pages available the user would like to see in the first 10 pages, in the first page. Okay? If you knew that set, then you could compare this against that set and say to which extent they overlap. The more they overlap, the better. Because we are always assuming that what the user wants to see is the ground truth. So it is what we would like to return to the user. Okay? We like, in some sense, to please the user. I don't say this is right. I'm just saying that that is what a search engine will try to do. Now, how can I do this? You cannot do this in general. You should have to be in the minds of the users. Sometimes what a search engine, or let's say anyway, information retrieval companies do, is that they make user studies. So they collect a population of users, for example, through Amazon Mechanical Turk, and they ask the users to submit queries, for which, in a sense, they are allowed to pick from, say, 100 different results, and they ask the user, okay, tell me which are the top 10 results you would like to see. And then they will have the top 10 results, the search engine results, returns, and then they can compare the results of the search engine against the results the user would have liked to see. Okay? They do this sometimes. Now, how am I going to measure how good, if I have this information, so I know from a sample of users what they would have liked to see in the first position, how can I decide how good my result list is? I need a numerical measure, right? Normally, what you do, you have two measures of quality. We will come back to this. Don't worry. But what is called precision and recall? Maybe you encountered them already. I don't know. They happen more and more frequently to be used in the common language. Not so frequently, but from time to time they do. So, in particular, what is precision? Precision normally is defined as a fraction of retrieved documents that are relevant to the user needs. For example, let's say these should be 10 results. Yes, of course, as usual. The first 10 pages are results. Here I have been returned 10 documents. How can I compute precision? The question is, out of these 10 documents, how many you consider relevant for the queries? In this case, you is me. Okay? And I can go on. I mean, for example, this is relevant, I think, this is relevant, this is relevant, this is relevant, current keys. This is relevant, actually. I could say, well, I don't know if this is relevant, wow. I mean, in this first case, I would say all of them are relevant. So in this case, precision would be 1. But now assume for a moment that I say, no, this is not relevant as a user. In that case, I will have that 9 out of 10 are relevant. In that case, my precision would be 0.9, which, by the way, is not bad. Okay? And then there is recall. They are subtly different. So precision tells, out of the documents returned, how many of them were relevant for the query. Recall answers another question. Out of the 10 million and more documents, some of them will be relevant to oil spills. I don't know which of them. In order to know that, I should sit down for the next months, probably, with 10 more people, check every document and decide, yes, this is relevant, no, this is not relevant, and so on. Eventually, I would come up with a list of documents out of the 10 millions that are relevant. Okay? So recall tries to answer the following question. Which fraction of these documents did you return? In my case, I returned 10 documents. Let's say the first page is 10 documents. So in the first 10 page, I have at most 10 relevant documents. Let's say that all of them are relevant. So I have 10 relevant documents. I should have returned, if I had to return in the first page all the relevant documents, perhaps let's say that in this collection there are, I don't know, 20,000 documents which are relevant to the topic. In that case, my recall would be 10 over 20,000, okay? Which is very low, but in this case, it cannot be very high. I mean, if I have 10 results in one page, and I have 20,000 potentially relevant documents, my recall will never be very high, okay? So, how can I increase recall? I return more documents, of course. The more documents I return, the more relevant ones I get. Eventually, if I return all the documents, my recall will be 1, because the results will contain all relevant documents. Unfortunately, if I increase the recall, I will be adding a lot of rubbish, documents that are not relevant for the query, so my precision will drop, right? So recall and precision there is a trade-off normally. The higher precision you want, the lower your recall, okay? So what should I prefer, precision or recall? Well, that depends on the application. For example, if my idea is that I'm just interested in what happens, or mostly interested in what happens in the first page of results, then I will try to maximize precision. Okay, so I return 10 documents, but I want them to be relevant for the document. If I'm interested in other applications, instead, there are other applications in which instead I might be interested in recall, because if there is something, I want to be able to find it. For example, we are recently looking at some application in, which has to do with medicine. It's called with precision medicine, in which you want to identify potentially cancer-associated genes, in which you want to find potential genes. So in that case, you are interested in recall, even if precision is not very high. Okay, but in this case, for example, I would mostly be interested in precision, because the number of results I'm going to return is 10 fixed. And out of those, I want to have as many relevant ones as possible. Okay? We'll come back to precision and recall, don't worry. I mean, but just to expose you initially to two very important accuracy metrics. Okay? And then I will tell you also why very often we are not using accuracy, which is itself an index, but they're not very popular in search engines, okay? I will tell you why we are not using it. Now, let's begin with some real meat now, finally. So, as I was telling you earlier, actually what we're going to say applies to document collections. Now we happen to be interested in web documents, but documents have been around for quite some while. I would say 5,000 years before Christ, at least, right? You know, in Mesopotamia, yeah? That's pretty old stuff. They were on stone, carved, actually not even on stone, on clay, carved on clay, but that's also documents. Now, how would documents be around 1620? For example, you could ask the following question over a digitalized collection of Shakespeare's works. Which plays of Shakespeare contain the words Brutus and Caesar, but not Cleopatra, Calpurnia? Is it clear, the question? So the documents that contain both Brutus and Caesar, but not Calpurnia. That's a basic question that you can answer. And the system should retrieve these documents, okay? How are you going? This is called Boolean retrieval, in the sense that your queries are just conjunctive or disjunctive forms of single terms. How are you going to do that? This is one way of doing this, right? You do grep. So when you write grep, it means this. Grep. The command, the Unix command grep. You have your command, you pass to the, you look up for these two words, and then in a second stage, you filter out whatever contains also the word Calpurnia, okay? Is there a smarter way to do this or not? You are too pessimistic. You are too pessimistic. Maybe there is a way. I mean, so first of all, this can be a bit slow for large document corpora. Why? Because if you think in a way that appears a sort of sequentiality, so you first of all, for example, pick a document and you want to understand whether or not the document contains both Brutus and Caesar. So essentially, very simply, you might begin with, first of all, you have to consider all the documents. Within every document, you should start to look for pairs, Brutus and Caesar, right? For the occurrence, you have to check that both appear. Then you take the document, add it to the potential collection. At the end of the first pass, after doing this for all documents, you would have to do a second filtering step in which you remove all documents that do not contain Calpurnia. To decide that the document does not contain Calpurnia, you have to check the entire document, right? Not is very bad. So, my God, doesn't look very nice, especially if you have, for example, 3 words, an end of 3 terms, checking that a document contains 3 terms. That's a bit boring, even more boring. I mean, you can do it, of course, but it's doable. I'm not saying it isn't. But maybe there is some smarter way of organizing your web corpus, your corpus, so as to answer this query more efficiently. Huh? Maybe even linear size. I have not said it. Maybe even linear time in the number, in the total size of the documents that you are going to consider. Maybe certain documents you don't even need to consider and you know from beginning. How is that possible? Well, depends on how you organize your data, okay? So let's start, as usual in these cases, as people do this. I mean, these things have been designed by people who were doing, algorithms or computer scientists anyway. So they begin with, they take a problem, they start to come up with an algorithm with a solution, then they, at some point, realize that given the data size, the first solution they had in mind is not really going to work because of efficiency, but it has some nice ideas behind. So they try to refine it. They try to make it more efficient till they come up with a very nice data structure. So let's begin by being stupid. So if I wanted to think of a very naive way of doing this, how could I go about? I could go about in the following way. I mean, after a few hours of thinking, perhaps. Of course, a posteriori, everything is easy. You have to come to this idea first. Now, let's consider what is called a vectorial representation of a document. So essentially, let's say, this is a snapshot, of course. Every document is a vector. Is a vector of terms that appear in it, okay? So on the left side, so rows, we have the terms. On the columns, we have the documents. So in this case, the vocabulary is very poor, just a few words, whereas Shakespeare vocabulary was much larger. But just to give you an idea. So what can I do? Well, actually, in principle, I can put, for example, just, I can consider a term document matrix, which is an incidence matrix. So let's say I put a 0 if a word does not appear in a given document, I put a 1 otherwise. If I want to be more accurate, instead of a 1 or 0, I will put the frequency. Notice from now onward that very often in information retrieval, the term frequency is misused. So we say frequency, but we mean count. So very often when you say the frequency of a word, you are meaning the number of times a word appears in a document. Normalization is implicit, okay? Is it clear? Okay. But anyway, in this case, incidence matrix. Columns are the documents, and rows are the words. Assume that you have this matrix stored in your memory. You process the documents once and for all to build this matrix. Now, it's a double array, if you want. Now, do you see a way of answering, let's say, Brutus and Caesar efficiently? Only Brutus and Caesar for now. Yes or no? A bit more efficient than grabbing and every document and so on. What can I do? So notice one point. Brutus and Caesar, you can look at this matrix by columns or by rows. If you look at the matrix by columns, these are documents. These are binary arrays representing occurrence of words in documents. If you look at them as the matrix as rows, these are just, again, occurrence vectors, but they give you a different information, the complementary information. They tell you which documents contain or not which words, right? So, which are the documents containing the words Caesar? The first, the second, the fourth, and the fifth, and the sixth. I mean, all documents but the Tempest, right? Oh, that's interesting. Now, which are the documents containing Brutus? The first, the second, the fourth, and the fifth. How can I quickly compute the subset of documents that contains both? I just AND the two rows, right? How long does it take to AND two rows? Linear, in the number of documents at most, which, notice, is very often, no. It can be very large. In the case of Caesar's works, it's much less than the number of words. Shakespeare's vocabulary was very big. So, very unlikely, he didn't try it thousands of works, but he could use thousands and thousands of words. So in this case, the query could be answered very efficiently. Yeah? You just take those two rows, you AND them, and then you look up the corresponding documents, and you're done. You see that? Yes or no? Who is unhappy with this? Hello? No one is unhappy? Everybody's happy? Yeah? Yes, 3 seconds to be unhappy. 2, 1, everybody's happy. No? Something missing?
The not Calpurnia. We just done Brutus and Caesar.
Yeah, now you want not Calpurnia. Ah, okay, not Calpurnia. Okay. Which documents should I consider? I should consider this, right? Because Calpurnia doesn't appear. I should not consider this, because Calpurnia appears. You know what I can do? I just negate that row, and then I take the AND again. End of the story, right? You see? So we have transformed. Actually, it was an AND. We just take the negated. And again, it is a linear in the number of what? In the total length of the query. In this case, in the number of columns. In the total number of columns. Yeah, in this case, it would be 2 times the number of columns, because if I'm working not in parallel, sequentially, I will first AND, for example, the second and third row, and after that, which takes linear time, and after that, I will AND the result with the negated of the fourth row, which again takes linear time, right? So let's say in the order 2 times the number of columns, right? But still, it's linear. Linear is less than linear. We have to do something else. We go to a different realm, which exists, but it's not the topic of this course. Okay? So, this idea is nice. So, search engines are using this idea. Yes or no?
The memory is cost of memory and in
You see that matrix? It looks harmless. Poor little matrix, right? So that matrix has to be somewhere, and it should be accessed fast, right? Now, if it is Shakespeare's work, maybe. If maybe Shakespeare using, I don't know, 20,000 words times how many works? In the 100, let's say, less than 100. 20,000 to 100,000, 2 million entries. Come on, we can do this. We waste a lot of space because there are many zeros here, but who cares, right? It will fit here. We can do this. But now let's try to and we can go on with Shakespeare like this. But what happens when your collection is bigger? So let's say for 1620, the search engine would have been perfect. Okay? You give them simply the term document matrix, and let's say with a mechanical computer, they would do the job, essentially. Okay? There was no Turing machine back at the time, but there were very nice automata. If anyone had invented an automata like this, they could have answered such queries, more or less, maybe in minutes rather than fractions of a second, but they could have. But now, today, maybe we have bigger collections. So let's pick a slightly bigger one, 1 million documents. That's not a big collection, okay, to be clear. So if you want to have a reasonable web corpus, you have to consider something that is at least 50,000 times bigger, at least, meaning the main pages, then there is multimedia content, and so on and so forth. So, okay, but this is, let's say, medium, small, medium-sized. This, in a web information retrieval conference, this would normally be considered small, medium. Small to medium, more to small. Let's say each document is about 1,000 words, okay? Keep in mind this now, I mean, these are more or less, these numbers refer to a document collection that was considered by the authors of the book just to provide students with some data to play with. Keep these numbers in mind now, because at some point they will become important. So 1 million documents, remember, each document more or less is using 1,000 words. It doesn't mean it is 1,000 words long. It is using the vocabulary of 1,000 words. This can be true, for example, if your web documents are news agency posts, okay? News agency, Reuters, Associated Press, relatively short documents with a moderately sized vocabulary, okay? Now, let's say that every word takes about 6 bytes. How do you compute that? Well, you take into consideration every letter, let's say, is 1 byte. Then you take the average length of an English term, English word, and then you consider the distribution of English words. That's how you get 6 bytes in average. Then you have to include spaces, punctuations, you put everything together and you get that every document more or less, every word more or less can be considered to be 6 bytes long, so that every document more or less will be 6 kilobytes, roughly. If you put this together, already your document collection, you discover 6 gigabytes. Wow. Small, already 6 gigabytes. So this is something to consider, because if you are storing the web, or a big portion of the web, it means that your 6 gigabytes are going to become something much, much bigger. So you have to organize them in some way. Of course, you have a data center, sure. But the size, you don't want things to be on secondary storage too much, because otherwise everything becomes slower. So, you have to organize your memory, your primary memory in some way. And assume that if you consider all the words appearing in at least one document, you obtain that the number of distinct terms can be 500,000. You say 500,000? So do languages have 500,000 words? No, they don't. But nowadays, they don't. Languages do not contain 500,000 words. But I don't know what this is. I have no idea what this means. I just randomly typed 10AK, and then I get 1 oak. So apparently 1 oak is something. This must be stay connected, exclusive mailing list. I have no idea what this is, really. But this means that Google has an idea. So it has to keep track in its web corpus of the existence of this stuff. So it means, it means that 10AK is a word in this particular web corpus vocabulary of Google, okay? So it means that actually the vocabulary you have to consider when you want to search a document collection nowadays includes a lot of other stuff, acronyms, special number sequences, even telephone numbers very often, right? For example, you want to find out whether the unidentified call you got was spam or not. You go on Telos and look it up. Yeah, that's again. So you give a phone number, unidentified phone number to Google, and if it is spam, for example, aggressive advertisement, very often it's somewhere. So it means that there is some document corresponding to that number, right? That contains that number. So 500,000 entries is not incredible, actually. Okay, so with this big collection, now let's assume that you want to do this trick. We want to do this trick here with that collection. What is going to happen? Can you tell me how large that matrix is? 500,000 terms, 1 million documents, 500 billion, correct? Yeah, 500 billion entries. They are not going to fit here, okay? On this, not on this machine, not on many machines that I'm aware of. Is that clear? Okay. Why? So there is no hope. Now I would like you to honestly answer the following question, trying to guess as little as possible. There is no hope of solving this problem. Actually, there has to be, right? Otherwise, we wouldn't be here. Anyway, how do you fix this issue? You have to be a bit smart. You have to take a closer look at that matrix. How do you fix it? It's sparse, right? Is it true that it is sparse? Well, this matrix, yeah, definitely looks sparse. But let's say this matrix here. Let's go over the data again. Let's think that we want to write down that matrix, right? Of course, we are speaking about average, but that tells you what is going to happen more or less all the time. So let's think of one row of that matrix. Let's just take those data. I have 1 million documents. So one row of this matrix will have 1 million entries, right? And now let's look at a specific document, one particular document, or let's say the average document. How does the row of the average document look like? Notice that I was specific, average document, not the worst case document. If we are engineering, we still consider worst case analysis. Of course, the worst case document will contain all possible terms. That is what worst case analysis tells us, and we are finished. We stop here, we say, no, sorry, you cannot do that. Maybe this worst case analysis is nice for certain things, but perhaps not for everything. So what does the average document look like? Each document is about 1,000 words. Each document is about 1,000 words. Maybe I was looking at the rows. The same will apply to the rows, but let's look at the columns, perhaps. Every document, 1,000 words. 1,000 words. So this is 0.5 times 10 to the 6. Out of this, how many entries are non-zero for the average document? More or less 1,000, right? More or less. So this is all zeros with a few exceptions. Okay? Of course, the average document. It means if you take the total entry, the total number of ones, and you divide by the number of total entries, you get that ratio. Okay? So only one entry in 1,000 in the average is going to be a 1. It means that in principle, that matrix is almost all zeros. And as you know, probably, if you ever use some more advanced package of Python, sparse matrices can be represented efficiently, right? How can I represent a sparse matrix? Because that is how we get to the main data structure used in information retrieval, I would say, perhaps. Yes.
Linked list.
Linked list makes sense. Yeah, there is going to be some list. There is going to be some list. So look at this. What could I do here? If I wanted to give a sparse representation of this matrix, what could I do?
Or just a hash. Hash map.
Hash map. Your colleague says hash map. Or what? I am not saying you're wrong.
Index or the key.
What is the key?
The key is the value of the word.
The word. Okay, your colleague says, listen to me, use a hash map. So something that represents a dictionary as an abstract data type or a hash table, if we want. Hash map. You see that? In Python, you would use, this would mean a dictionary. In Java, yeah, you have a hash map, then you have subclasses and so on. But anyway, your colleague is saying strategically, the key is a word. Great. Fantastic. I mean, I completely agree. So, let's say this is your hash map, hash table if you want. The key is a word. For example, Brutus. Or whatever. Good. Normally, a hash table is a structure-based array. You have a hash function. From the word, you find one entry quickly. Okay. And what do you find here? Say it louder. Fine. What will you find there?
Each value of the index row.
Yeah, but for example, let's take Calpurnia.
0, 1.
You find 0, 1, and so on. You could have a bit vector, but
Or just 1.
you're almost there. Come on. Remember, you want only represent the ones and not the zeros. What are you going to find?
Just the name of the document.
You find, let's say, for Calpurnia, your first entry would be Julius Caesar.
Yes.
So
The name of the document.
the next one would be Julius. The next one would be nothing, right? In this case, you would be saving. Of course, you need some extra storage to store the map, but the map, you know, so the vocabulary, it's linear in the size and the number of terms. So 500,000 terms, I can build a hash map for that. That's not a problem. Even 1 billion terms, I can do that. The problem is 500,000 times 1 million. That's the problem that I cannot afford. Okay? But in this way, I have to add an extra cost which is proportional to the vocabulary size. But then I'm only recording the ones. Or let's say whatever is different from 0. Actually, I will put a lot of information in every entry. Okay? So in this case, for Brutus, I will have, let's say, the list. So let's say the names of the documents in which the term Brutus appears. Actually, in 1620, we would have the names of the documents. Today, we have a numeric attribute associated to the document. So every document is mapped into a number using a hash, is hashed into a number, which is called the doc ID, document identifier, and that is what appears in the corresponding entry. Okay? And then we can start reasoning about this. So, and that is called an inverted index. Why is it called an inverted index? Because normally when you represent a document, you represent, in some sense, the key is the name of the document or some identifier of the document, and then you have an array of the words it contains. Here we are doing the opposite. We are representing, for every word, we are having the identifiers, a list of the identifiers of the documents that contain the word. Why are we doing this and not the opposite? Because this looks similar to the matrix we were using. You remember we want to do the ands, yeah? Of documents between the vector, the rows of documents that contain a given word or don't contain a given word. Yeah, we'll get, next lectures are going to be on this. Don't worry. So, let's try to summarize what we have seen. The basics of an inverted index. There is a lot to say still, okay? We are just at the beginning. But let's say we have come up, beginning with the term document matrix, we have come up that certain queries, find all documents that contain both this term and this other term, can be best answered if you're able to do the AND of the queries, assuming they provide only binary information. Then we observe that this matrix can be too large, but that most of the times it is very sparse. So we essentially are representing that matrix in a compressed way. How do we do this? We use a data structure which is called an inverted index. So the inverted index, it is called an index because the entries, it is basically a hash table with a linked list. Every entry is a linked list. So essentially every entry, every linked list, which is called, by the way, a postings list, represent one row of the term document matrix. Is that clear? In a compressed format. We will see a few examples. So let's begin with some terminology. So for each term, you can think of it as a word for the moment. Essentially, we store a list of all the documents that contain the term. Is that clear, the first part, to everyone? Is that clear? So for example, we will store the list of all documents or the document of the identifiers of all documents that contain the word Brutus. Is that clear? But then how do you find the documents? That's another. Once you have the document identifiers, you will keep your document somewhere. And whenever you have to access a document, you use the doc ID to access the document on the database. That's not a problem. Is it clear what I'm saying? I mean, here we only want to answer queries. We want to know which documents contain which term. In order to know this, we do not keep to store the entire document, right? We only have to need to keep the information on whether the term appears in the document or not, and perhaps how many times it appears. That's all we need to know. So for every term, we will keep a list of the documents that will contain the document, that will contain the term. Actually, we keep a list of the document identifiers. So the identifiers of the documents that contain this term. How we define the identifiers and so on, for the moment, we don't care. You can think of the identifiers as integer numbers. Every document is assigned an integer number. That's all. Okay? It's a document serial number. And they are called doc ID. I mean, the term is so used that people don't say document identifier anymore. They say doc ID. Whether or not we can use, instead of a list, a fixed array, well, that depends. First of all, with a fixed array, perhaps you are wasting memory. On the other hand, when you have to insert a new document, which means that you have to update the posting list for all the terms that are contained in the document, an array may be. So essentially, if I have to add a new document that, for example, contains the words Brutus and Caesar, I have to change these to arrays. And you know, modifying an array is always a bit a pain. You have to build a new array, copy the contents. It's better to use a list, okay, with pointers, you know, okay. I mean, you can use fixed arrays, but then from time to time you may have to double or to increase the size of the array. So, Actually, this is what we have. Inverted index. The terms actually collected in a structure that you can think of as a dictionary or as a hash table, something equivalent, which means that you can look up one entry very easy. For example, if I have a query with Brutus, accessing the corresponding entry here is fast. It takes amortized, so in expectation, constant time. Yeah? That's why I use hash tables. Constant time access. Maybe not worst case, but average. So finding the right entry here is easy, and then you have the access, immediate access to the list of documents that contain the term. So every document, how is, for example, for Brutus, how is this list organized? These are the doc IDs. As you see, they are the doc IDs which can be thought as integers, even if they are strings. I mean, you can sort strings, right? They are normally arranged in increasing order or decreasing order. I mean, but they are ordered. Why? Because, are you okay? No, your phone, good. Okay, why? Because there is a very deep reason for doing this. But anyway, they are sorted, okay? So, for every term, this allows you to uniquely identify the documents in which this term appears. Once you find, you have the doc IDs of the documents in which it appears, you can find the documents themselves. For example, the document corresponding to this doc ID might be doc11.txt on your disk, okay? Just to give you an idea, a practical idea. So you don't need to store the entire document. I mean, the documents will be somewhere on your disk. But in order to process this stuff in main memory, because this data structure will be in main memory, it is enough just to know the doc IDs, okay? Is everybody okay so far? I guess you have a number of questions. For example, why are these sorted? How did you do it? How do you build this? How do you build the inverted index? I didn't say that. I'm just saying what I want to have in order to be able to answer queries in an efficient way. I have to say the rest. I have to say how I build this data structure, which is the inverted index, and also I still have to say how do I efficiently answer a query like Brutus and Caesar and not Calpurnia using this data structure. I didn't say that yet. Okay, so if you feel you are still missing something, it's fine. You are still missing something. I'm just beginning. Okay, I've just introduced the inverted index. For now, dictionary of terms plus list, linked list for every term. And every linked list contains all the documents. When I say all the documents, I mean the doc IDs of all the documents that contain the term. Okay? Let's try to make a stupid exercise, the equivalent of what we did with the matrix before. Assume that I wanted to have the documents, to know all the documents that contain the term both Brutus and Caesar. What could I do? Don't think now, what is the algorithm, write down. Try to use your intuition. What can I do? Since the two posting lists are sorted, I can start from the beginning, right? For example, if Brutus is contained in doc ID 1, well, doc ID will be also at the beginning of Caesar's posting list, right? So I can, in principle, scan the two lists according to increasing doc IDs. Whenever I find the match, I add the corresponding document to the set of documents that contain both, and then I proceed. For example, I will begin with two pointers both on these positions. I will notice that the corresponding doc ID is the same, so I will say, okay, 1 belongs to the result list I should return. Then I will advance both pointers to the next doc ID, and I will notice, 2 also belongs to this subset of documents that contain both Brutus and Caesar. And I also add 2 to the result list. Then I do the same here, right? And then I also add 4. Then I jump to the next position, and I notice that these two entries are different. And I say, what happened here? Well, here I have a gap. Clearly, since I proceeded a line up to here, it means that Brutus is contained in this document, but not in this one, and vice versa. Okay? This is the slightly harder part to deal with, but you will discover that there is an old algorithm that you saw in your second year, I think, as part of another sorting algorithm that can be used to this purpose. Actually, it is used. Okay? I will not say it now. But just to give you an idea of where I want to get. So, let me see how much time I still have. I have 5 minutes. I will try, I'll look for a nice landing spot to stop the lecture and leave it up to Professor Vitaletti next Thursday. Now, so let's just give some terminology. This is called the dictionary. Essentially, it's called a dictionary because it is a dictionary. It is the collection of the words you have, and also because it is intended as a dictionary in the sense of the abstract data type. You know, a dictionary is a data structure where you can essentially have 3 insertion, search, deletion, right? That's what you can do. Look up, especially looking up. And this is a dictionary. It is intended to be a dictionary. And then each entry is connected, leads you to a list, which is called a posting list, of all the documents IDs, identifiers, that contain the term. Of course, I write the doc IDs, but you can easily suspect from now that these entries will not just contain the doc ID, probably. They contain a lot of other information. For example, how many times the term appears in this document. There can be actually every posting, which is every entry, can contain hundreds of bytes of information or more. Okay? But still, it's hundreds, it's not megabytes of information. So, how do I build an inverted index? I'll give you an idea. This is not the real, you will see this a bit more in detail. But building an inverted index, I mean, it seems, I guess in principle, all of you have an idea of how you build it. You know how to build a dictionary. I mean, you know how to build a hash table. You start adding keys, and then for every term you have add all the terms. But when you're doing these things for web corpora, the document collection is very large. So even very simple operations can become very expensive. So efficiency is a premium. So you're dealing with documents residing on secondary storage, and you have to access secondary storage. Accessing secondary storage is very slow, right, with respect to main memory. If I have to access 1 million of documents, I cannot do 1,000 passes over the documents, you know? I cannot access the entire corpus 1,000 times. It will take ages. So I have to be careful. I have to use every pass of the document collection to collect as much information as I can. You see what I mean? I cannot access the same, I mean I can, but this will be terribly inefficient. In order to build my inverted index, I cannot afford accessing the same document, let's say, 200 times in average. Because this will be a lot of work. I mean, I will waste a lot of time. Access to the disk is in the order of milliseconds. If I do this 100 times for every document, and I have 1 million documents, it's going to take ages. I cannot do that. So I have to be careful. So you begin with a document collection, so documents in digital formats on your disk. And first of all, you start making one pass of all the documents to collect all the terms they contain. So that you have to do. If your documents collection is 6 gigabytes, you will have to scan 6 gigabytes. But you try to do it once. So you scan the entire document collection to extract words. In this case, they are called tokens, linguistic units. So for example, friends and friend will be 2 different tokens to begin with. And who does that? Well, a tool which is called tokenizer. Not by chance. Then you apply what are called linguistic modules. For example, if I have, when I want to analyze document collections, I mean, some words are actually have the same semantics. For example, countryman with a capital C and countryman with small c, actually it's the same word. It happened that countryman appeared at the beginning of the document. This is generally true. Of course, there are exceptions that you may try to take into account. For example, when countryman with capital C appears in the middle of the document, then maybe the capital C has some special meaning that you may want to keep into account, okay? But in general, let's say that many words, many different words can correspond to the same meaning. For example, Romans with capital R and plural, or Romans with small, I don't remember now, with normal R, with normal R can correspond both to the stem Roman, and so on. So you apply linguistic models that bring to modified tokens. I'm not giving the details now, just to be clear. And then you build the inverted index on the refined vocabulary. Okay? So your inverted index will not contain the original words, but just what are called either lemmas or the stems. In Italian, we say the linguistic root of the words. Okay? For example, you will have friend, meaning whatever has to do with friends, friend or friendship. And you could have kin for whatever has to do with kinship, and so on. And the initial stage of text processing, I will leave it up to Professor Vitaletti, because our time it was enough for today. To take in, I guess.